So in this video, we're going to use Excel to help us find the area under the standard normal distribution. So when we see something that says the probability that z is less than 2.31, what we're really saying is if 2.31 is right here-ish, okay, we're finding the area all the way to negative infinity. So what we're seeing here, the shaded region, is when z is less than -1, but less than 2.31 would be all of this area all the way under this curve from here. So it's always a good idea to think about approximately how much area should that be. Well, we know from the empirical rule that at 2 standard deviations from the mean, we know that this is 50%. So this is 0.5 from negative infinity all the way to the mean to here. Then we have another 34%. So when we're here, we're at 0.84. Then this is another 13.5%. So now we're at 0.975. So we know that this number should be a little bit bigger than 0.975. Again, let me erase all this stuff. We know that up to 2 standard deviations above the mean, that's 97.5% of the area under the curve. So that's 0.975. So we know that the area below 2.31 is going to be even bigger than 0.975. Not much bigger, but bigger. So what's the formula that we're going to use to find this? Well, there's a formula called normal distribution. So it's norm.dist. And when we start that function, you can see we get an x value. So we want an x value. In this case, that's going to be the 2.31. We need the mean, which this is the standard normal curve, so the mean is 0. The standard deviation for the standard normal curve is 1. And then we're going to use the cumulative distribution function, which is true here. And we get 0.98955. Now, if we were going to use false in this would actually give us the same probability mass density function that we used last time when we did the binom dot dist. It actually produces the same values for a discrete random variable. So we're not interested in that. We're interested in the area under a standard normal distribution. So that's what we have here. All right, so let's do another one. Now we want to find the probability that we're greater than 2.56. So 2.56 is right around here. That's probably a little farther than I need to be, right about there. That's 2.56, okay? And we want this area right here. So again, we know that the area up to 2.31 was 0.989. So that means this area is going to be small, okay? It's going to be really small. Because it's just this little bit off to infinity. It does go off to infinity, but the way that we find this probability, or this area, is similar to how we found the probability of the binomial distribution when things were greater than. So what we're going to do is we're going to say, well, this is 1 minus the probability that z is less than 2.56. And I know I didn't put an equal to sign, and you might be wondering, well, shouldn't it be less than or equal to 2.56? The area less than 2.56 or equal to 2.56 are not different areas. and this has to do with calculus. The area of a infinitely thin sliver, thinner than this line that I drew here, under the curve is actually going to be nothing. It's negligible. It's so close to zero that we call it zero. So we don't have to worry about any equal to signs for any of these problems. Okay, it's just going to be the same thing regardless. So if you want to think of this as less than or equal to, that's fine, but you don't have to. So the probability that z is greater than 2.56, which is the area under the standard normal curve, is the same thing as 1 minus the probability that we get less than. Now, why would I have to rewrite it this way? Well, because as shown by the shaded region, our norm.dist function only finds the area below the given value all the way to negative infinity, which we know once we get past -3, there's hardly any area here anyway. It's just 0.0015 is all the area that's less than -3. So it's almost nothing. So I need to find the probability that z is less than 2.56, and then I'm going to do 1 minus that. So we're going to do 1 minus, again, norm.dist. My x value is 2.56. My standard deviation is 0. And my mean is 0. My standard deviation is 1. Excuse me. And I'm going to put a true here. And we get 0.00523. Now, if it helps you to have the mean written down, so let's say we took all these notes here, put them down. So if it helps you to know what the mean is and what the standard deviation is, and to have those in a cell and reference those cells, that's fine. And if you want to do what we did with the normal, the binomial distribution, put your x value in a cell as well, that can help. Okay, so now in this next example, this is a little bit more difficult. We want to find the area from -1.1, so right to the left of this here, -1.1, and then to 0. Okay, so since we know that half of the area is below here, from here all the way to negative infinity, I'll draw it out a little bit longer, all the way here, this is just 0.5. And so, if we can find the shaded region here below the red line, to the left of the red line, and then we take all of the area, 0.5, and subtract out the shaded region, we'll get the area that's in between. So if we find this shaded region, and then we take all of this, 0.5, and subtract the shaded region, we'll get this part right here, which is what we're looking for. We're looking for the area in here. That's some good shading right there. All right, so let's go ahead and do that. So we're going to take, again, we're going to take 0.5 because we know that's what it is. I mean, I could always do, let me just show you real quick, norm.dist 0, 0, 1, true. Oop, comma, true. And look what that gives me. It gives me exactly 0.5. So we don't have to do all that out. We can just say 0.5 minus norm.dist. And now my x value is negative 1.1. The mean is 0, standard deviation 1, true. And I get 0.3643. All right, so now thinking about the same thing, let's find the area that's just greater than negative 0.1, negative 1.1. So let me erase some of this stuff. So we're looking for this area, all of the area greater than 1.1. So that's going to be all the area here to infinity. Keeps going. So if we do, if we find this shaded region like we just did, this time instead of doing 0.5 minus that, we're going to do 1 minus that. So again, this is 1 minus the probability that z is less than 1.1. Sorry, negative 1.1. So that's just going to be 1 minus norm dot dist. We're going to do negative 1.1, 0, 1, and then true. And that gives me 0.86433.